Welcome back to 15-Minute Math. So this is going to be just a video that gives another example of how to find a definite integral using the definition of the definite integral. So recall that the definition of the definite integral is this. We're going to find the limit goes to infinity of the summation, where I is 1 to n, f of x star dx, oh, not dx, I'm sorry, delta x, okay? And remember, delta x is the width of each subinterval. X star is just some sampling of some point inside that subinterval. I think everything else is pretty much explanatory. So we've done the rectangle approximation thing, and I've shown you a picture here on the right side. So if I use 4 subintervals, the approximation is, this, 5 3/4. But clearly that's an overestimation. In fact, I've got the exact value on the screen. When we do our definition here, our integral by the definition, I should say, this is the answer we'll get. But it's always nice, I still think it's nice to look at a picture. When you're setting up a definite integral, even by the definition, I still think it's great to look at a picture. It's still great to think about, okay, where are my corners hitting the function? You know, how can I set... The troublesome part is setting it up. Once you set it up, you're just going to crunch through some algebra. So let's go ahead and let's do this thing. First of all, let's find out what delta x is going to be. Maybe I should switch colors for this. We'll maybe do our work in blue. So delta x is the width of our function, our subintervals. And remember, that's b minus a over n, which in this case is going to be 2 minus 0 over n, which is 2 over n. Now, another thing that we want to figure out before we get into it is, how do I represent x star? And remember, you can choose how to represent it, because we're going to take n to be infinity, which means the difference between left and right endpoints is 0. But it does make a difference when you think about how you're going to represent that point. And so if I'm going to use right-handed endpoints, it looks to me like I'm going to be taking, let's just do the 4 here. I'd be taking f of 1, I'd be taking f of 2, f of 3. I'm actually just going to start at whatever rectangle number I'm at, and I'm going to jump the width of a rectangle after that, and then the width of a rectangle after that. And so it looks like to me, I could represent this as the width of a rectangle times whichever rectangle I'm currently on. And remember, in our definition, we're using I to represent that. That's kind of our indexing variable. So x star is going to look like that. And so we're going to be taking, let's plug all that in. We're going to be taking the limit as n goes towards infinity of the summation I equals 1 to n of f of 2I over n times 2 over n. All right. Now remember, in this particular case, n stays constant until we take the limit, of course. So for summation purposes, we can move that outside our summation. So we're going to take the limit of 2 over n times the summation, and now we can go ahead and plug in our f of whatever. So it's going to be 2I over n squared plus 1. Okay, so now we can just square out our 2I over n there. Oh, my pen is trouble connecting. Hang on just a moment. There we are. Okay, so we'll have the limit as n goes to infinity, 2 over n times the sum, I going 1 to n, 4I squared over n squared plus 1. Just like we've done before, we're going to go ahead and split the summation. So since we have a binomial, we can split the sum into two different sums. So we'll just have the sum from 1 to n, 4i squared over n squared, plus the sum I goes to n, 1. Okay? Now remember, I, in the summation, I is the variable that's changing. The n is not changing. And so this 4 over n squared is a constant. By the way, this 2 over n multiplies all of that. And so we'll have 2 over n times, let's go ahead and bring that 4 over n outside the summation. And so we have something that looks like this. That was just a terrible signal. There we go. That's a little better. All right, cool. Now we're ready to evaluate those sums. So the limit as n goes towards infinity, we'll have 2 over n, and then 4 over n. Now if you remember our rules from the previous video, if I'm taking the sum from 1 to n of I squared, that's going to be n plus 1, 2n plus 1 over 6. And then if we think about it this way, if I take I starting at 1 and going to n, and I just have 1 over here, it's, you know, we'll have I goes 1, 2, 3, 4, 5, 6, 7, all the way to n, but I always just have 1. So basically I have n copies of 1, and so that's just going to be n. Okay. So moving on. Let's see here. We'll leave this 2 over n for the time being. Let's go ahead and multiply this out. 4 over 6 is the same thing as 2 over 3. So I know I'm going to have 2/3 something. Well, 2 over 3n something. And when I multiply that out, I should get 2n cubed plus 3n squared plus n. Maybe I could center up that 3n a little bit. And that's plus n. Okay. Like we did before in the previous video, we'll just go ahead and split that monomial divisor. And so it's going to look something like this. 2 times 2 is 4. So I'll have 4/3, and then I'll have n cubed over n. Okay. And I think, as I look at this, I think I've lost track of an n. And I found my missing n. And it's all the way up here. Look at this. This was 4 over n squared. And then when we moved that outside of the summation, that just became 4 over n for some reason. That makes no sense. So that really should be 4 over n squared, 4 over n squared, which would make this 2 over 3n squared, which makes this n cubed over n squared, actually. Okay, so moral of the story, it's super easy to leave powers of n off, but try not to do it. It really messes you up. So, okay, so let's distribute. So 2 times 3 is 6. 6 over 3, that's just going to be 2 n squared over n squared. Plus, distribute again, we'll have 2/3. It looks like n over n squared. Plus n. All right, we're getting there, we're getting there. So what can we do now? I guess we can multiply this 2 over n into our quantities here. And as we do this, let's simplify our n's. For example, when I multiply this in, it's going to be 8/3, but I'm going to get n cubed over n cubed, right? Because I'll have n squared and then another n makes n cubed. And n cubed over n cubed just cancels, right? So I just have 8/3. And then here I'm going to multiply, I'm going to have 4, but I'm going to have n squared over n cubed, which is 1 over n. And then here I'll have 4/3 plus n over n cubed. Oh, that's just going to be 1 over n squared. Okay, so I've got that term, that term, that term. I just need my last term. It looks like I'm just going to end up with 2 because the n over n will cancel. And that looks like what it turns out to be. Now, when I take the limit as n goes to infinity, anything with an n in the denominator is simply going to go to 0. And so I'm just going to get 8/3 plus 2, which is 8/3 plus what? 6/3, I suppose, which is 14/3, or what would that be? I guess that would be 4 2/3, which is 4, oh no, didn't have the pin activated, 4.6 repeating. And if you recall, let's scroll back up to the very top, and we've done a lot of algebra. That's what Desmos gave us. I copy and pasted this from Desmos, FYI. 4.6 repeating is exactly what I came up with. So if I want to know the exact area under x squared plus 1, and I'm looking from 0 to 2, so if I don't want these little errors here, I just want the exact value, it turns out to be 4 2/3. And this is the process to get it. Now, again, there are shortcut methods, and we're going to learn those shortly. But it is good to know why those method works. You know, what's the underlying mathematical machinery? And that's why we spent a couple videos going over that before we get into how to expedite the process.